So here we begin our exploration of transformations being onto and one-to-one mappings. And our first definition that we are going to explore together is that of an onto mapping, which is also known as a surjective mapping. So we say that a mapping T from Rn to Rm is onto or surjective if each vector B in the codomain, Rm, is the image of at least one vector x in the domain, Rn. So in other words, what is this saying? Well, in other words, the equation defined as the image of vector x under the action of t equals vector B has at least one solution. And at least one solution meaning vector x in Rn. So if this equation has at least one solution, we know the mapping is onto. So a couple of alternative ways to say that a transformation is onto or surjective are the following. So the first one is that the range of the transformation is equal to the codomain of our transformation. So if the range equals the codomain, that transformation is onto. So with this in mind, we can come up with another way to say that a transformation is onto. We can say that every vector in the codomain is an output of some input vector x. In Rn, or in the domain. So if every vector in the codomain is an output of some input vector, then the range of the transformation equals the codomain of the transformation, and your transformation is onto. Now, what about some equivalent ways to say that a transformation is not surjective or not onto? Well, keeping the equivalent ways in mind, the first way is, well, the range of the transformation is going to be smaller than the codomain. So if the range of our transformation T is smaller than the codomain, then your transformation is not onto. Another way to say that a transformation is not onto is to say that there exists some vector B in Rm, or some vector B in the codomain, such that the equation defined as the image of vector x under the action of t equals vector B does not have a solution. So if this equation does not have a solution, then your transformation is not onto. And last but not least, one more for good luck here. If there exists a vector in the codomain that is not an output of any input vector, your transformation is not onto. So if there exists a vector in the codomain that is not an output of any input vector, then this implies that the range is smaller than the codomain, and thus your transformation is not onto. The next definition that we are exploring together is that of one-to-one or injective mappings. So we say that a mapping T from Rn to Rm is one-to-one or injective if each vector B in the codomain Rm is the image of at most one vector x in the domain Rn. So in other words, what is this saying? Well, it's saying that the equation defined as the image of vector x under the action of t equals vector B has at most one solution. So if the image of vector x under the action of t equals vector b has at most one solution, we know that this mapping is 1-to-1. So some alternative or equivalent ways to say that a transformation is a 1-to-1 mapping are the following. So we can say that for every vector b in the codomain, or for every vector b in Rm, the equation defined as the image of vector x under the action of t equals vector b has either 0 solutions or 1 solution, mainly vector x in Rn. So for every vector b in Rm, if the equation defined as the image of vector x under the action of t equals vector b has either 0 or 1 solution, we know that this transformation is a 1-to-1 mapping. Another way to indicate that a mapping is 1-to-1 is to say that different inputs of the transformation have different outputs. So different inputs of our transformation t have different outputs. So in other words, each vector x in Rn is mapped to a different vector in the codomain. So another way to say this would be to say that if the image of a vector u under the action of t equals the image of vector v under the action of t, then these two vectors must be equal. So in other words, then vector u must be equal to vector v. If this holds true, we know that our transformation is a 1-to-1 mapping. So what about some equivalent ways to say that a transformation is not a 1-to-1 mapping, or is not an injective mapping? Well, we could say that there exists a vector b in the codomain, Rm, such that the equation defined as the image of vector x under the action of t equals vector b has more than one solution. So if there exists a vector b in the codomain such that the equation defined as the image of vector x under the action of t equals vector b has more than one solution, then we know our transformation is not a 1-to-1 mapping. Another way to say this is that there exists two different inputs of our transformation that have the same output. So there exist two different inputs of t, or more inputs of t, that have the same output. If this holds true, we know that our transformation is not a 1-to-1 mapping. And last but not least, another way to say a mapping is not 1-to-1 is to say that there exists vectors u and v in the domain such that vector u does not equal vector v, but the image of vector u under the action of t is equal to the image of vector v under the action of t. If this holds true, we know that our transformation is not a 1-to-1 mapping.